We're looking at our second session for week 2 of this continuous learning, and it is exploring properties of logarithms. You've already seen a video talking about the basics. We're going to go into more detail. With this first one, we have a logarithm is an exponent. Nope, I haven't selected my pencil. And some logarithms are used so much that they are called common logarithms and natural logarithms. Your calculator only uses common and natural logs. Common logarithms are logarithms with a base of 10. And, as I drop my screen, it is log base 10, more commonly known just as log. Natural logs are logarithms with a base of e. And they are written as, well, if we have log base e, that's the same thing as our natural log. What is e? E is a constant used as the base in the exponential formulas. E is an irrational number approximately. If you look at the completed notes, I've extended it all the way out. I'm just going to do through the 10,000th place. 2.7183. Since logs are nothing more than exponents, the rules come from the rules of exponents. You will notice this connection as you explore the properties of logs. If we were doing this in class, you would be doing this on your own and there would be an exploration, but you're not, so here is the video with the notes. Using your TI graphing calculator, evaluate the following. Well, the log of 1 is just 0, and the natural log of 1 is also 0. Write this as an exponential expression. That's saying 10, because that's my base, to the 0 equals 1. E to the 0 equals 1. So when we have this first situation, a log of 1 always will equal 0. On here, log base b of 1 is always going to be 0. The next set, log 10 equals, well, when you put that in your calculator, you see that equals 1. Ditto natural log of e, that equals 1. Rewritten, that's saying my base of 10 to the 1 is equal to, well, of course it's just equal to 10. Anything to the first power is itself. E to the 1 is equal to e. Next rule, log of b base b, I probably should have said it, log of base b to the b, whatever, always equals 1. So if your base and what you're taking the log of are the same, then that will always equal 1. On your calculator, what we want you to do is plug these in and see what you, well, you should see this. I have the base and the component the same, so I know it's going to equal 1. Number 6, it's also 1 because it's base 200. My solution is 200, so my exponent has to be 1. Pause the video, see what you get with the next 3 for part 7 and for part A. When you plug log 3 plus log 8 into the calculator, make sure you close those parentheses. You get 1.380. A common thing would be to say, hey, I'm adding 2 logs, so I'm just going to add what the solutions are, 3 and 8. So if I do log of 11, I get 1.041. Those aren't the same. And then, look at that. If I multiply 3 and 8, I do get the same thing. So I'm going to highlight that, saying, nope, let's use purple. Hey, look, I got the same thing for both of those. Let's make that bigger. Let's do the same thing over here. What do you think are going to be the same? I get 2.996, and then I get 2.197, and then I get 2.996. Interesting that when I multiply, I end up getting the same solution, taking it log or natural log. The next rule. Oops, we're on the next page. The next rule, which follows exactly from what we just did. So when we add, oops, logs, we are actually multiplying the numbers. So on this one, I have log base b for both, and I'm saying log base b of a plus log base b of c. That's really saying log base b of a times c. Rewrite the following log expressions. Well, I have log base 3, and I know I'm multiplying those two because of this addition sign, which is going to be log 3 of 42. Again, I want to multiply the 4 and the 9. If you look at the completed notes, I go into more specifics. I'm just going to go straight into it. So I have log base 8. 4 times 9 is 36. Natural log, it's the same thing. I'm going to take what's inside, multiply those together, and I get the natural log of 5x. The last one in the situation, log base m of y plus log base m of 3. Well, it's going to be log base m of 3y. Using your graphic calculator to evaluate the following. So what happens if I subtract two logs with the same base? When I do the first one, log 10 minus log 2, I get 0.699. If I actually subtract them, I get 0.903. Those aren't the same. And then I get 0.699. How can I go from 10 and 2 down to 5? Think about it. So let's continue this and be consistent. Let's highlight this. Let's highlight that. Over here, natural log. If I take natural log of 15 minus natural log of 5, I get 1.099. If I actually subtracted 15 and 5, I get 2.303. How could I go from 15 and 5 down to 3? Just like how did I go from 10 and 2 down to 5? Well, regardless, I still get the same answer. I know, some of you have already seen the answers and gone on and figured it out. But when I subtract, I'm really dividing the numbers. So here I have log base b of a minus log base b of c. That's really log base b of a divided by c. Rewrite the following log expressions. I will show more work on 15. The rest I will just go through and do. So this says I have log base 3. Because I'm looking at subtraction, it's going to be 42 divided by 7, which gives me log base 3 of 6. I have log base 8, and I'm taking 15 divided by 2. When I do 15 divided by 2, I have a common factor. I can pull out a 5, so I'm left with log base 8 of 3/5. Over here on 16, natural log, 2x divided by 18. Oh no, in the notes I forgot the x. I'll fix that. 2x divided by 18, well, I'm just left with x over 9. How did I get x over 9? 2 is in common in both the numerator and the denominator. Last one, log base m. If I take 20 and divide it by 4y, I'm left with 5 divided by y. Once again, using your graphing calculator to evaluate the following. If I have log of 3 squared, I get 0.954. Well, what if I separate that? Because that's really like saying log 3 times log 3, which is an addition problem. Well, that's 0.954. Addition with the sense of logs. Last one, 2 times log 3. Hey, that's 3 different situations where they are all the same answer. What do you think you can guess on number 20? You got it. They are all the same as well. So let's go to the next page. This is the last bit when we have our situation. The rule 5 When I have log exponents, the exponent can be moved to a coefficient. And then I'm just going to multiply. So in this one, my exponent is in, so that becomes my coefficient, and then I multiply by log base b of a. Rewrite the following log expressions. Here's my coefficient, so I'm just going to pull that in front, times log base 3 of 7. Right here, 8 is really 2 cubed, so I'm going to pull the 3 out front, and then I have log base k of 2. My exponent is 5, so I have 5 times the natural log of x, and then 81. We know that's 3 to the 4th, so I have 4 times log base m of 3. The rules, you know that we typically don't write it like this, but because of our programming, it's written like that. If you wanted to change it, it really should look like this, log of u divided by v. Let's go to the practice page. My suggestion, pause the video, try to do at least 25 through 30 on your own, see if we get the same answer. If not, we'll figure it out. Once again, I have those rules on the far side. This is the same thing as log of u divided by v, written a little bit more appropriately. So I'm going to write this out. Use the log rules to expand each expression. Well, these are multiplied together. I don't like that. These are multiplied together, and you have the rules. If they're multiplied, then I'm really looking at an addition situation. So I have log base 3 of 3 plus log base 3 of x. I'm not finished there because in this situation right here, I have the base and the solution are the same, which means I know that this changes to 1 plus log base 3 of x. And there's my final answer. I'm kind of getting tired of green, even though it's my favorite color. Let's move to red and blue. I have two situations here. I have division and I have addition. So let's look at this. I'm going to do the division first. So I have log of 2x minus log of 5. But then multiplication means I'm really adding, so I get log of 2 plus log of x minus log of 5. The next problem, I have multiplication and I have an exponent. I'm going to focus on the multiplication and then worry about the exponent. So I have log base 7 of x squared plus log base 7 of y. Now my exponent can be pulled out into the coefficient, so I have 2 times log base 7 of x plus log base 7 of y. Next one, it's just like 27, but instead of multiplication, we have division. So I'm going to look at this. Oh, apparently I forgot to change the color, so we're going to do blue here. Log base 2 of x squared minus log base 2 of 4. I have a coefficient, which I can, I have an exponent, which I have as a coefficient, can throw in front. And then 4, I can simplify that. So I have 2 times log base 2 of x minus log 2 of 2 squared. This becomes 2 times log base 2 of x minus 2 times log base 2 of 2. Well, guess what? Log base 2 of 2 is just 1, and 2 times 1 is 2. So my final answer is 2 times log base 2 of x minus 2. Okay, we're going to go back to red. Natural log, I have a square root, so I really have a coefficient. I'm going to look at it like that. So I have the natural log of xy, this whole thing to the 1/2. I'm going to write it a little bit differently than what I did on the completed notes, but we'll still get the same answer. Because I have 1/2 as an exponent here, I can pull that as a coefficient. So I have 1/2 times the natural log of x times y. But x times y inside the natural log is really like addition, so I have 1/2, and it's going to be times this entire quantity. The natural log of x plus the natural log of y. If you want to see it broken down into more pieces just to look at the answer, look at the completed notes. Otherwise, you get the same thing that I did here. Okay, this last one, number 30. I'm going to be looking at subtraction because I have division, and then I'll look at the addition part after. So I have the natural log of 1 minus the natural log of 2x squared. Well, the natural log of 1, which we've learned, log any base 1, that's always going to equal 0. So I'm left with 0 minus the natural log of, I'm going to do this in parentheses because I'm going to split it apart. Natural log of 2 plus the natural log of x squared. Well, I can essentially just get rid of that, but make sure I keep the negative and distribute it through. So then I get negative natural log of 2. Distribute that negative through, I get a minus. The exponent can become my coefficient, and then I have the natural log of x. There's my final answer. Last two, 31 and 32. When we're looking at these, we want to simplify them as much as possible, and then we can plug in or substitute in what we know to figure out the evaluate for 31. On 32, we'll look at it and I'll show you. So 28, I can rewrite 28 to be log base b time, which is 4 times 7. This is the same thing as log base b of 2 squared plus log base b of 7. This is 2 times log base b of 2 plus log base b of 7. This is my expanded form, so this is the first part. The next part, it says expand each log expression, then use the information above to evaluate each expression. So I'm just going to take that information and substitute it in. So I have 2 times, well, log base b of 2 is approximately 0.6310, plus log base b of 7 is approximately 1.7712, which I'm just going to say equals, when you put that in your calculator, you get about 3.0332. So there's that evaluation. On this next one, when you're looking at certain situations, you want to simplify the expanded form and then look, because whatever is inside as your solution is actually going to be equal to what's inside the solution over there, since I have the same base. So x plus, I have log base 7x plus log base 7x. Well, that's really like saying x times x, which is log base 7 x squared minus log base 7 of 3 equals log base 7 of 12. And when I look at subtraction, that's really division, so I have log base 7 of x squared divided by 3, which is equal to log base 7 of 12. From here, I have the same situation. I know they're equal, so I know I can say x squared divided by 3 equals 12. Multiplying both sides by 3, x squared equals 36. Taking the square root of both sides, I get x is equal to plus or minus 6. So from here, when we have our plus or minus, you learned with Mrs. Beyer that you cannot have a negative. Your argument has to be greater than 0. So our final answer is x equals 6.